We've talked about finding the sums of finite geometric series, and finite geometric series, again, the difference between finite and infinite is just that finite has a stopping point. That stopping point is the 6th term or the 5th term. It's that nth term that we said this series is stopping at. So infinite geometric series is just going to be a geometric series that continues on technically until infinity. So there is no stopping point. It just goes on and on. So the sum of an infinite series is called a partial sum if it's just to the first n terms. But the partial sums of an infinite geometric series may approach a limiting value. So it says, consider the infinite geometric series a half plus a fourth plus an eighth plus a 16th plus a 32nd plus continuing on. Find and graph the partial sums for the first, second, third, fourth, and fifth term. And then it wants us to describe what happens as those term numbers are increasing. So, your first term and your sum for the first term is just simply going to be 1/2. Sum of your first terms is 1/2 plus 1/4, first term plus second term, which equals 3/4, and all of these will be reduced. Sum of your first three terms equals 1/2 plus 1/4 plus 1/8, which equals 7/8. And if you guys want to keep them as decimals, that is okay. Sum of your first four terms is going to be 1/2 plus 1/4 plus 1/8 plus 1/16, which equals 15/16. And then the sum of your five terms, the first five terms. And again, well, not again, but if you guys want to, you don't have to write out every single term. If you know that the sum of the first four terms is 15th, 16th, okay, well, that's that sum, plus the fifth term, which is 1/32. So the sum of your first five terms will be 31/32. So as our term numbers get higher and higher, we started at 1/2, then we get to 3/4, and now we're down to 7/8, and then 15/16, and then 31/32s, or 31/32. Your value for your sum is getting closer and closer to 1. So as n increases, as your term number increases, S of n, or your sum, approaches 1. So let's go ahead and graph this. And it gives us the intervals for us. So the sum of your first term, S sub 1, is 1/2. And then 3/4. And then 7/8, 15/16, and 31/32. So they're getting really, really close to 1. And again, that's sort of like we've talked about with asymptotes, where it's approaching. So the same thing here. A limit is a value that your function is approaching. So in this case, our partial sum for n equals 1, 2, 3, 4, and 5 is approaching the value of 1. So that's what it's talking about for partial sums approaching a limit. It's talking about a number that is approaching. Okay. So the sum of an infinite geometric series. So that means the entire infinite geometric series, not just part of the infinite series. If you know the first term, a sub 1, and the common ratio, r, then you can find the sum of that series by saying, okay, the sum equals a sub 1, your first term, divided by 1 minus your ratio, the value that it's decreasing by. Provided, here's the important part, that the absolute value of r is less than 1. So, your ratio has to be smaller than 1. It can't be increasing. if your ratio is greater than 1, then the series has no sum. Because what's going to happen is if your ratio is being multiplied by 1.5, it's increasing. It keeps increasing. If something keeps increasing, it never has a stopping point. It's just going to literally increase forever. So you won't be able to find a distinct sum for it because there's no end point for you to find the sum of where it ends. So you guys have to be careful. If that is the case, if your R is greater than 1, if your ratio is greater than 1, then it has no sum. So you can only find the sum if your ratio is less than 1. And again, that's the absolute value. So we're not including that negative sign. We just want the absolute value of that ratio. So it says find the sum of the infinite geometric series. It wants the sum from 1 to infinity with the rule 3 times 1/4 I minus 1. So your 1/4 is your ratio. The 3 is your A sub 1. So what would the sum be? Well, the ratio is 1/4. The ratio is smaller than 1, so we can find the sum, and we need to do that. So the sum is going to equal 3, and I'm going to just erase this quick, because that's your first term, over 1 minus 1/4. So that's going to equal 3 divided by 3/4, or 0.75, however you guys want to write it. Which equals 4. So the sum of this infinite series is going to equal 4. Every term added up is going to equal 4. So what about number 3? Negative 1/2 plus 1/4 minus 1/8 plus 1/16. Well, negative 1/2 times what gets you to 1/4? 1/4 times what gets you to 1/8? 1/8 times what gets you to 1/16? And again, if you guys have geometric, you can work backwards. You can say, okay, this divided by the term before it gets us what? That gives you the ratio. But in this case, I know that it's times 1/2 or 0.5. And I know that if it's giving me the series, that the first term there is going to be my first term, negative 1/2. So I know the ratio, and it's actually negative 1/2. Because it goes negative, positive, negative, positive. And the only way to go back and forth is to keep multiplying by a negative. So the sum is going to be negative 1/2 divided by 1 minus negative 1/2. So you get negative 1/2 divided by 1.5, which is 3/2, which gives you negative 2/6. Which reduces to negative 1/3. So the sum of that entire series, because, I mean, you can imagine those decimals and those fractions are going to start to become pretty small. So the entire series will only equal or add up to negative 1/3. So remember, you can find the sum as long as your ratio is less than 1. If your ratio is greater than 1, your series is going to, your terms are going to continue to increase, and you'll never be able to find a sum because it's just going to get larger and larger. We can also use the sum of an infinite geometric series to be able to write repeating decimals in fraction form and figure out what they would be in fraction form. What we have to do is figure out what is it being multiplied by in order for this to continue to be repeated. So if you guys are looking at this, 0.131313 repeated, it has 2 decimal values or 2 decimal places that get repeated. So 2 decimal places puts us in the hundredths spot. So we could say that that first term, or the first repetition of 0.13 really equals 13 times 0.01. So if we wanted the entire decimal, 0.13 plus 0.13 plus 0.13, each spot would have to have zeros in front of it. So what happens is each place value, so the second 0.13, would be 13 times 0.01 squared. And your last repetition would be 13 times 0.01 cubed. And what happens is you guys can add them all up, and that gives you that repeating decimal. We add them, so it's a sum. So the ratio is what you're multiplying by, the 0.01. So if you guys were to do this, you could say that your A sub 1 would be 0.13, the first repetition, and your ratio that you multiply by to get 13 to a decimal is 0.01. So if you guys are trying to find the sum, it would just be 0.13 over 1 minus your ratio, which gives us 0.13 divided by 0.99. So we don't want these decimals within fractions, so if you multiply them by 100 over 100, also equal to 1, doesn't change the value, just changes the way it looks, this becomes 13/99, and that would be our repeating decimal as a fraction. So a repeating fraction is really just a sum of repetitions in different place values. That's it. So if you guys had, say, 0.333, that would be 3 times 0.1. Or if you had 0.321321, that's 321 times 0.001. It's because you're in the thousands. You're just looking at the place values to see what that ratio is that you're going to be multiplying by. Alright, if you guys have any questions, it was a pretty quick lesson, but let me know, and you guys, then we'll continue with the next lesson tomorrow.